Okay, so here's another easier example of using work in the problem. Paige is the tallest player on South's varsity volleyball team. She is in spiking position when Julia gives her the perfect set. The 0.226 kilogram volleyball is 2.29 meters above the ground and has a speed of 1.06 meters per second. Paige spikes the ball doing 9.89 joules of work on it. Oh, it's just giving work. Nice. Determine the speed of the ball upon hitting the floor on the opponent's side of the net. Okay, so again, I want to have a nice little picture. Okay, so here's this. Here's the ball. Okay, right? She's actually adding a force to it. She's adding work into the ball, adding energy into the ball. Okay, and then at some later time, it's about ready to hit the floor. Okay. All right, so let's do ball, earth. We don't want to put Paige in the system, right? Because she's doing work on it, so she stays outside the system. All right. Initially, right, this ball is moving. Okay, oops, that's weird. It's moving and it's above the ground, no springs. Okay, and then Paige is going to do work on it, right? So she's going to add work by Paige. She's going to add some kind of energy to the system through her hit, okay? And then later on, right, the ball is at the ground level, no springs, no air resistance or anything. So then it's only going to have speed, okay? So I can see here, if I add up all of these energies, 1, 2, 3, 4, 5, 6, this is going to have to be 1, 2, 3, 4, 5, 6. Okay, because after I have to have the same amount as I started with. Okay, and again, the numbers don't matter. It's just whatever you want to do. Okay, so when I set up my equation, I have my initial energies plus the work done, right? Because I'm going to add work into the system equals the final kinetic energy. Okay, and then I can go ahead and fill in my equations. Okay, I can just leave this as work, right? I don't have to do force times distance because they just give it as work. So there's no need to split that apart. Okay, 1/2 mv final squared. All right, we can't cancel the m's because the work doesn't have one, so that's sort of a bummer. Okay, so now I just have to crank out some math here. It was moving 1.06 squared plus 0.226, 10, or 9.8 if you're using WebAssign, 2.29 plus the work done, okay, equals 1/2 0.226 VF squared. Okay? All right, and now I just have to, like, do this all stupid math. See, you'll be to the point where you're just like, can't we just leave it in variables? This is a hassle. Every time you have to use a calculator, it's just fraught with disaster potential. 226 times 10 times 2.29. If you use 9.8, it'll be slightly different, but don't panic. 8 plus 9.89 equals 0.113 VF squared. I'm already starving. I don't like this new lunch schedule. I guess I could have just eaten lunch, but... Okay, 0.127 plus 5.18 plus 9.89. So 15.197, that's joules on that side. Okay, divided by 0.113. Radical. Okay, and I'm expecting it to be much faster than it was before, right? And indeed, it is much faster. Okay, there, 11.6. Okay? All right, so that's that one, and then hopefully in class we're going to have time to do these two. Okay, the only difference with these, right, is notice they're giving you the coefficient of friction. So that means when you do the work is the force of friction, you're going to have to do your mu Fn there. Okay, right? Same thing on this one with an inclined plane. This one's a little more complicated because there's multiple parts to it. Okay, but if it's on an inclined plane, right, and they give you the coefficient of friction, you got to think back and do some force manipulations there. Okay, all right, and then the rest of this, there's a WebAssign and then some other little practice-y things, and then there's more than this next class too.